As you already hopefully remember, the periodic table currently is arranged by increasing atomic number. The purpose of this lesson will be to explore the elements in the periodic table and discuss the topic of periodic trends. When we first started this topic, we had to complete this reading guide using the textbook. There are 4 trends that you need to be aware of for this unit, including atomic radius, ionic radius, ionization energy, and electronegativity. It might be a good idea if you can get out this worksheet while you listen to this video. The first trend I want to review is atomic radius. Well, you might be asking yourself, what does an atomic radius mean? Well, if you've got your atom and you've got protons and neutrons in the nucleus, around the nucleus you've got these shells and energy levels where electrons can be found. So I'm going to put my electrons out here. So again, in the nucleus you've got protons and neutrons, and in the orbitals or their energy levels outside you've got electrons, which are the negatively charged particles. Now, atomic radius is just how big is this element or atom. So, as with the radius of a circle, you measure the radius of an atom from the center of the nucleus to its outermost energy level. Now, if you look at the periodic table, energy levels increase, or so the number of rings would increase as you move down the periodic table. So every row on the periodic table represents another ring being added to the atom. So it makes more sense that as you move down a column in the periodic table, the atomic radius gets larger. So if you're from top to bottom, your larger ones are at the bottom. So larger, smaller. Now, when you go across a row from left to right, as you increase atomic number, moving left to right, you also increase the number of protons and electrons. Well, you guys know that when you have something that's positive next to something that's negative, they attract. So they would come close to each other. Well, the more positives and the more negatives you have, the stronger that attraction is. So the tighter they can be pulled to each other. So even though there's more protons and electrons in an atom, the number of rings doesn't change. So it's not as though we get more rings around it. The number of energy level stays the same. So what's happening is that the more positives can pull more tightly on the negatives. So really they all move in closer, which makes the atom smaller. That being said, your larger elements then or atoms would be on the left side of the periodic table, while your smaller would be on the right. So to sum that up, when you look at the periodic table, your largest atom would be the bottom left. The smallest atom would be the top right of the periodic table. So the general trend would be as you go down and to the left, you get larger. Ionic radius is similar to the atomic radius, except now we're not talking about an atom. We're talking about what happens when an atom loses electrons or gains electrons. So I'm going to draw an example of a helium atom. Actually, I take that back. I'm going to draw a hydrogen atom. So I've got my 1 proton in the nucleus and my 1 electron on the outer ring. Well, hydrogen likes to form a 1 positive ion, which means it wants to kick off this electron. So hydrogen becomes 1 positive. So when hydrogen loses that electron, it no longer needs this ring for parking spots. So when you take away an orbital or an energy level, the radius gets smaller. So the trend is that if you are an atom that forms a metal, or excuse me, a positive ion or a cation, your cation would be smaller than the original atom. That being said, everything that forms cations is on the left side of the periodic table, the metals. If we draw a stair-stepper line here, everything on the right side of the periodic table here, they form anions. Well, if you're an anion, that means that you are gaining electrons. So let's draw a nitrogen atom. Got my protons and neutrons. And then my energy levels. I've got, let me see, 1, 2, 3, 4, 5, 6, 7. So this is a normal atom of nitrogen. When nitrogen becomes an ion, it likes to have a -3 charge. So 3 electrons from somewhere else will come in and join up in this outer energy level to have a total of 8 valence electrons, which means that nitrogen forms the anion nitride when it gains the electrons. That being said, as you get more electrons at an energy level, what starts happening is that these electrons that are close to each other here don't want to be close to each other, so they start repelling. So this inner electron is going to push this guy away. So as it pushes him away, this energy level is all going to experience the repelling force, which means that your atom will get larger. So to sum that up, anions are larger than the uncharged atom, because especially if you have to add another energy level to fit in electrons that you're adding. So the general trend with cations and anions is that cations are smaller than the original atom and anions are larger than the original atom. Well, what does that mean for the trend across the periodic table? Well, just as with atomic radius, your largest cations are down here in the bottom left. Now, at this stair-stepper line separating the metals from the nonmetals, these guys still all form cations. Well, they would be your smallest cations. So this is largest cations and smallest cations. The nonmetals now follow the same trend in that it's still bottom left are larger, but now these are larger anions and smaller anions. And remember that noble gases don't actually form ions, so those aren't really included in the trend. So to sum up overall with the periodic table, some diagrams show several arrows, so I'm going to show you a couple examples. With ionic radius, you get larger as you go down a column and larger as you go left along a row for both cations and anions. So these arrows that I'm drawing represent an increase. The next trend I want to talk about is ionization energy. Ionization energy is quickly summed up by calling it the amount of energy I would have to put into removing an electron from the atom. Now, depending on the atom, it could be easy or difficult to remove an electron. So this ionization energy is energy required to remove an electron from the atom. So now if I wanted to take this electron off, how hard would I have to pull? Well, if you think about it, as you go down a column in the periodic table, you increase the number of energy levels or rings around an atom. Well, if you were holding on to something and you had it held very far away from you versus really close to you, you would be able to hold on to it more tightly if it was close to you. So the further away an electron is, or the farther it is from the nucleus, so the greater the number of energy levels, the harder it is for a nucleus to hold onto it tightly, meaning that it wouldn't be anywhere near as hard to remove this electron as it would be to remove this electron. So that being said, this would have a low ionization energy because there's a lot of distance between the center of the nucleus and the outside electrons. So the closer the electron is to the nucleus, the harder it is to pull it away. So that trend, if we look at the periodic table, this would be your lowest energy, or the easiest to take away. The hardest to take away is your nonmetals, including fluorine, as they are very close to the nucleus and don't want their electrons to be taken. Now, as you move left to right across the periodic table, you again are increasing the number of protons and electrons. As you increase the number of protons and electrons, again, that charge, the forces that come from all the positives and the negatives attracting each other, make a tighter bond. So this was increasing as you move from left to right, because the more protons and protons and electrons you have in an atom with the same number of energy levels as everyone else, the tighter you can hold on to your electrons. So the overall trend with the periodic table is that your highest electronegativity elements are in the top right, your lowest are in the bottom left. So as a general trend, it's harder to pull away electrons from atoms in this area versus atoms in this area. The last trend I want to talk about is electronegativity. Electronegativity means if you're an atom and you have protons and neutrons and electrons, what are the chances, or how attractive would you be to an electron on another atom that's looking to leave? So now the question is, how hard would your protons in the nucleus work to pull this guy to your atom? Now, the trend for electronegativity is very similar to that of ionization energy, in that your overall trend is that the lowest electronegative elements are in the bottom left of the periodic table, and the highest electronegative elements are in the upper right hand of the periodic table. The reason for this is that as you go this way on the periodic table, as you go from left to right, you're suddenly starting to begin to form anions. Well, if you're an anion, that means you want to gain electrons. Well, if you want to gain electrons, that must mean that you are working overtime to get this guy over here, because you want to gain electrons. So as you move from left to right, you go from forming cations to forming anions, so you want to gain electrons. If you're a cation, so if you're on the left side of the periodic table, you want nothing more than to lose electrons to become like a noble gas. So are you going to work very hard to pull this guy over? No, you're going to work hard to shove this guy out. So the most electronegative elements are in the upright corner of the periodic table, and the lowest are in the bottom left corner.